All right, let's get energized. Because today, we're talking about circuits, the pathways of electricity that make our modern world tick.
From smartphones to spaceships, it's all about circuits.
Exactly. And in this deep dive, we're going to unravel the mysteries of the two most fundamental types, series and parallel circuits.
And to make things even more exciting, we're taking you on a virtual field trip.
That's right. We're heading over to Okinawa Christian School International, where students are getting hands-on experience with circuits and multimeters.
These students are learning by doing. It's pretty cool.
It really is. So let's start with series circuits, which are the stars of today's lesson. Imagine electricity flowing through a single pipe, just like water.
That's the essence of a series circuit. The current, or flow of electricity, remains constant throughout. Each component, like a tiny light bulb called an LED, experiences the same electron flow.
So it's a continuous, uninterrupted path. But what about the voltage, the electrical pressure pushing those electrons along?
Voltage. In a series circuit, the voltage is divided among each component. Think of it like sharing a pizza.
Okay, so the more LEDs you add to the circuit, the smaller the slice of voltage each one gets. So does that mean they get dimmer?
You got it. The voltage gets spread thinner with each added component.
And what happens if one of those components, let's say an LED, decides to take a break?
Well, that's where the chain reaction aspect of series circuits comes into play. If one component fails, the entire circuit breaks.
Like a broken link in a chain, it stops the flow completely.
The students are actually seeing this firsthand in their experiments. They remove an LED and bam, the rest of the LEDs in the series circuit go dark.
Fascinating. Now, to really get a grip on what's happening in these circuits, the students are using these handy gadgets called multimeters.
They're like detective tools for electronics, helping us measure the invisible forces at work.
I love that analogy. So what exactly can multimeters tell us about a circuit?
Oh, they can reveal a lot. Multimeters can measure voltage, current, and resistance, giving us a clear picture of the electrical properties.
So they're like a Swiss Army knife for anyone working with electronics.
Precisely. And the students are learning how to use them to verify all those principles we just discussed about series circuits.
For instance, they can measure the voltage across each LED in their circuit, right?
Absolutely. And they're also discovering how to measure the total resistance of the circuit.
I remember learning that the total resistance in a series circuit is simply the sum of the individual resistances of each component.
That's right. It's like adding up the lengths of individual pipes to find the total length of a water flow.
Okay, that makes sense. But what about the current? How did they measure that with a multimeter?
Measuring current is a bit different. The multimeter actually needs to become part of the circuit itself, briefly interrupting the flow of electricity.
So it's like adding a flow meter to that water pipe analogy.
Exactly. The students are learning how to safely break the circuit, insert the multimeter, and get an accurate current reading.
And one of the key things they're observing is that the current in the series circuit is the same at any point along the path.
Just like a single-lane road, no matter where you stand along that road, the number of cars passing by per minute will be the same.
So in a series circuit, we have constant current, divided voltage, and total resistance. That's the sum of the individual resistances. It's a pretty good starting point.
It is. And the students are solidifying this understanding by actually building the circuits, taking measurements, and analyzing the data.
Talk about hands-on learning.
Yeah.
But are there any real-world applications to these concepts they're exploring?
Absolutely. One of the big takeaways for the students is understanding how the number of components in a series circuit affects its overall behavior. They've seen that adding more LEDs makes them dimmer because the voltage is shared among them.
Right, like that pizza analogy.
Yeah.
And they've also learned that if one component fails, the whole circuit goes kaput.
It's all connected, literally.
Speaking of connections, one thing that often throws people off is the concept of an LED's forward voltage.
Yes, forward voltage. Think of it as the minimum voltage needed to switch on an LED, like a threshold that needs to be crossed.
So it's not enough to just apply any voltage. It has to be sufficient to activate the LED. Makes sense. But how does this forward voltage affect how they measure resistance in circuits with LEDs?
That's where things get a bit tricky. Unlike a simple resistor, an LED's resistance isn't fixed. It changes depending on whether it's lit or not.
So it's a moving target, so to speak.
Exactly. This makes it difficult to measure the LED's resistance directly using a multimeter.
So how do they figure out the resistance if they can't measure it head-on?
They use Ohm's law. By measuring the voltage across the LED and the current flowing through it, they can calculate the resistance indirectly.
Ah, so it's like having a secret formula to unlock the missing piece of the puzzle.
You got it.
It's fantastic how they're learning to use multiple tools and concepts to solve these little electrical mysteries.
It's all about building those problem-solving skills, which are crucial in any field, not just electronics.
Now, we've talked about voltage, current, and resistance in series circuits, but how are the students applying these concepts to real-world situations?
Well, one thing they're learning is the importance of careful planning and construction when building these circuits. Even a small wiring error can lead to unexpected results.
It's like a recipe gone wrong.
Precisely. They're also learning about safety precautions when working with electricity, always double-checking connections, using the right tools, and never working on a live circuit.
Absolutely crucial lessons, especially for young, curious minds. But beyond the practical aspects, what are some of the broader takeaways they're getting from working with series circuits?
They're grasping the fundamental principles that govern how electricity behaves and how we can harness its power to make things happen.
It's about understanding the why behind the what, which makes learning so much more engaging.
Couldn't agree more.
So we've delved deep into series circuits, uncovering their unique characteristics and the challenges they present.
Now it's time to switch gears and explore the world of parallel circuits. That's where things get even more relatable to our daily lives.
I'm ready for that. Let's dive into parallel circuits and see what makes them so special. All right, parallel circuits, bring it on. You mentioned they're more common in our daily life, so I'm really curious to see how they work.
Okay, so think about your house. You can turn on one light without all the lights coming on, right?
Exactly. That's actually a great example.
Well, that's because houses are wired using parallel circuits. Each light has its own separate path back to the power source.
Ah, that makes sense. So instead of everything being connected in a single line like a series circuit, there are multiple branches. So does the electricity, choose which path to take?
It's not really about choosing. The electricity distributes itself among the branches. And a key difference here is that each branch in a parallel circuit gets the full voltage from the power source. Remember how in series circuits the voltage was divided?
Yeah, the pizza slices.
Exactly. Well, in parallel, each component gets the whole pizza, all the voltage.
So if I wire two LEDs in parallel, they both get the same voltage. Would they be the same brightness, even if one LED had higher resistance?
Yep. That's one of the cool things about parallel circuits. Components operate independently. They don't mess with each other.
Wow, I see why parallel circuits are so popular.
Yeah,
But what about the current? How does that flow in a parallel setup?
great question. So while the voltage stays the same across each branch, the current actually splits up among those paths, like water flowing through branching pipes.
So if one branch has more resistance, it gets less current.
Exactly. Current always prefers the easier path, the one with less resistance,
Yeah.
and the total current coming from the power source is just the sum of the currents in each branch.
Okay, that makes sense. So voltage is consistent, current splits. Now, how about the total resistance? Is it like series circuits where we just add up the resistances?
Not that easy. Total resistance in parallel circuits, it's a bit more complex. We can't just add because those multiple paths give the current different options, so the overall resistance actually goes down.
So it's like having extra lanes on a highway. More ways for the traffic to flow, even if there's a jam in one lane.
Perfect analogy. The students are learning a special formula to calculate the total resistance, which considers each a branch. It's a little more involved than series, but important to understand how the whole circuit behaves.
So are the students using their multimeters to investigate these parallel circuits? Measuring voltage, current, resistance, like before?
You bet. Same techniques, but the readings tell a different story. For example, they see that the voltage across each branch is equal to the total voltage from the power source, just like we talked about. Each branch gets the full voltage.
Makes sense. And the current readings, what are they finding there?
They're confirming that the current is indeed split up. They measure each branch separately, then add those currents together to check that it matches the total current coming out of the power source.
Like putting together the pieces of a puzzle. The voltage and current measurements all fit together to confirm how parallel circuits work?
Exactly. And they're also measuring the resistance of each branch, then using that formula to calculate the total resistance of the whole parallel circuit. Theory meets practice.
They're getting the full picture, that's for sure. Are there any experiments they're doing to really drive these concepts home?
Yeah, one cool thing they do is build a parallel circuit with multiple LEDs, then play around with adding or removing LEDs from different branches.
What happens when they do that?
They see that changing one branch only affects the current in that branch. The other branches don't care.
Oh, so it's like having separate light switches in different rooms. Turning one on or off doesn't mess with the lights in other rooms.
You got it. And this interdependence is a big reason why parallel circuits are so useful and show up everywhere.
I'm starting to see how these series and parallel circuits, although they seem simple, are the foundation of so much technology.
Absolutely. The students are learning principles that apply to everything from smartphones to, well, everything.
Okay, so we've covered the main differences between series and parallel circuits, the voltage, current, and how to figure out that tricky total resistance. But before we move on, any thoughts on why it's so important to understand these concepts?
It boils down to this. Circuits are the building blocks of pretty much every electronic gadget. From a simple flashlight to a complex computer, it all comes back to circuits.
So knowing about circuits isn't just for science class, it's about understanding how the world works, really.
Exactly. It's about going beyond just using gadgets and understanding how they do their magic. And maybe even designing your own solutions someday.
So it's about moving from just consuming technology to understanding and maybe even shaping it. And that all starts with grasping these basic ideas of series and parallel circuits.
You got it. And those students at Okinawa Christian School International are well on their way to becoming the next generation of inventors and problem solvers.
Now, before we wrap up our exploration of parallel circuits, is there anything else you'd like to add about the student's experience? Or about hands-on learning in STEM in general?
I think the main takeaway is that learning about circuits should be active, not just theoretical. They're building, testing, figuring things out, and using real data to learn.
It's way more engaging than just reading about it in a textbook. Like the difference between reading about riding a bike and actually riding one.
Absolutely. And this hands-on approach not only makes STEM more fun, it also builds critical thinking skills, problem-solving abilities, and shows how science, technology, engineering, and math all connect together.
It's about fostering that curiosity, that drive to ask questions and explore, and not being afraid to make mistakes.
Exactly. Programs like the one at Okinawa Christian School International are doing a fantastic job of inspiring the next generation of innovators.
It's so encouraging to see young people engage with STEM in such a dynamic way.
Okay, so we've journeyed through the world of parallel circuits. So we've explored both series and parallel circuits. And wow, it's amazing to see how these two fundamental concepts are the basis for so much of our technology.
It really is. And what's even more fascinating is how these seemingly simple circuits can be combined and arranged in countless ways to create such incredibly complex systems.
Yeah, it's like once you understand the basic building blocks, the possibilities are endless.
Exactly. And as those students at Okinawa Christian School International continue to delve into electronics, they'll discover how these building blocks can be used to create everything from, well, simple toys to sophisticated robots, even life-saving medical devices.
The potential is just mind-blowing.
Yeah.
And it all starts with understanding those fundamental concepts. You know, before we wrap up this deep dive, I'm curious to hear your thoughts on what makes this kind of hands-on learning so powerful, especially for younger students. Well, I think it really taps into that natural curiosity we all have, that desire to figure out how things work. When students can actually build circuits themselves, manipulate the components, and see the results of their actions, it really brings those abstract concepts to life.
It's like the difference between, say, reading about a bicycle and actually riding one, right?
That's a great analogy. You can study the mechanics all day, but it's not until you actually experience it firsthand that you truly understand how it works. And in STEM education, hands-on learning not only makes things more engaging, but also helps students develop critical thinking skills, problem-solving abilities, and a deeper appreciation for how science, technology, engineering, and math all work together.
Yeah, it's about encouraging them to ask questions, to experiment, to not be afraid of making mistakes along the way.
Absolutely. And programs like the one at Okinawa Christian School International are so important for nurturing those future innovators and problem solvers.
It's inspiring to see these young minds engaging with STEM in such a dynamic and meaningful way. So as we wrap up our deep dive into the world of circuits, what's one key takeaway you hope our listeners will remember?
I would say, remember that circuits aren't just lines on a diagram or components on a breadboard. They're the fundamental building blocks of our entire technological world. And understanding how they work allows us to truly appreciate the ingenuity behind the devices we use every day and to imagine what's possible in the future.
Well said. And who knows, maybe some of those future innovators are, right now, tinkering with circuits at Okinawa Christian School International, inspired by the lessons they're learning. the hands-on experiences they're having.
I wouldn't be surprised.
Well, that brings our deep dive into the amazing world of circuits to a close. We hope you've enjoyed this journey into the heart of electronics and that you're leaving with a newfound appreciation for the power and the potential of these incredible pathways of energy. Thanks for joining us.